conference. So from Tokyo, Sushi Saito will be speaking about rigid and dedicated.
Thank you for introduction. And I like as organizer for this invitation to give a talk. And also I like the organizer for this all efforts to organize this beautiful conference, which I've been enjoying so much. And so I'd like to invite all of you to just present. Yeah. And I'd like to thank all of you for coming to my talk. Even though this is, subject is rather singular, it's rigid space. And I don't know how familiar you guys are, but I try to make as much effort as possible to make it understandable. So this is joint work with Maurice Kurtz and Georg Tamme. Plus Georg. Okay, let me start with this motivations. So once and for all, I just fixed complete discrete variation field. And in this rigid setting, it's rather better to use this norm instead of the variation. So you fix like any real number less than equal to like this, and you just put the norm as the just C of the variations of K. Okay. So then, and this is not also some convention from rigid geometries. Integer ring is denoted like this. So this is now integer ring, which is now looks like this. So this is an element whose norms are less than or equal to 1. Okay. And here you have a prime element pi. I mean, that doesn't have to be prime actually. I mean, any element in this maximum ideal. And give yourself some formal scheme. So this is the formal scheme over this integer ring. And thus you get some pro system. So this is given by some Indo system of schemes, right? And so you get some pro system. Let's say, so this ring over N of the K, pro system of the spectrum, okay? And so this is like X to the N. So, in this talk, I just denote K is just like non-connected K pseudo, okay? So this is, this is denoted by the K continuous of this formal scheme. So this is pro spectrum. Okay. Why am I interested in this? This is because of this work of the Bloch and Kurtz and Mullo. So, among, so this is just special case of there are some kind of some more general theorems, but just let me state this special case. Okay, so this is a Bloch. And Kurtz and Mullo. So what this is what they say is the following. So if X is the formal completions of the abelian scheme, so assume. So any for abelian scheme. Over, let's say, K naught. So this case, we assume like a K of some formal power series. So this and the characteristic is 0. You have map from the algebraic K, K0 of X, and maybe tensor Q, and going to this lim. You take a lim over N of the K0 of the, let's say, this Xn. Okay, and take a tensor Q, And actually, this turns out to be not surjective in general. And you have to take eigenspace for the Adams operations. So this is for L. L is any number, okay? L square, and this L alpha star is induced by multiplication by L on this abelian scheme. Okay, and here you take the same things like this, and this is surjective. Assuming this, this implies Hodge conjecture for abelian varieties. That's the consequence of this more general theorems. They work on some kind of, they prove the formational part of the variational Hodge conjectures. And this is somehow like a remaining part, which says some kind of algebraization problem for this continuous K groups. Okay, so this is just concerns only K0, but like it would be nice to have some more general theories, some kind of alternative theory to just approach to this gadget. And okay, and yes, pardon? Yeah, yeah. Okay. Okay. So yeah, but you made some contribution. Yeah. Okay. And observation. So observation, actually this was later somehow like made precise by Matthew, but for this should use some kind of rigid analytic method. Rigid analytic case theory, whatever it is. So this comes from the following observation. First of all, recall this Reynolds theorem. So you have this, okay, I will recall this, what this rigid space are. I mean, there are several definitions, but like, I just adapt this most, like a classical definition, which is maybe intuitively easy to understand. But anyway, so you have, let's say, quasi-compact, quasi-separate rigid space over K. So this is a category of them. And you have now like a quasi-compact, topologically finite type formal scheme over this integer ring. And you somehow like localize by admissible blow-up. So admissible blow-up means like you just blow up in the center, contained in the defined by some power of either defined by power pi. Okay, so that maybe center is supported at some sequencing of the special fiber. That's what the admissible blow-up is. So it doesn't change the generic fiber. Okay, and there's some equivalence like this. Okay, that's the some consequence. I mean, this is a big some fundamental theorem in the rigid geometries, and now this procedure is descent. And I think this now this time, like Matthew, I think certainly deserves to be named here. So he did it like for characteristic 0. I mean, residual characteristic 0. So I mean, so this residual characteristic 0. So this residual field of these things, and also like recently Kurtz, Strunk, and Tame. Yeah. They show this procedure descent, which implies if your formal scheme, okay, is algebraizable, like some formal completion, okay, or some schemes of finite type of the integer ring, okay. In this case, so this is x over this integer ring, then cofiber of the k x supported on pi going to this k continuous of x I mean, this doesn't fill. Does not fill admissible blow up. That's sort of easy consequence of the procedure descent. Yes, here. Yeah, visualizer. You don't need it? But like this doesn't make sense. Okay. Yeah. Okay, and then, okay, so, yeah, because, I mean, maybe I can give you reason, because this is like push out of the k of the x going into the k of continuous of x, x of, maybe continuous of x, and this k of xk. And this fiber doesn't depend on the, this, doesn't feel this admissible blow up by procedure descent. So that's why. Okay, so that means maybe that's why you expect somehow like this, maybe this kind of things should be somehow like, pardon? No, you just take this, maybe this limit. This,
Here in the push-out, is k continuous of the x or the formal scheme?
Formal scheme, yes, formal scheme, yes. Yeah. So this means like somehow like this kind of things should be somehow like should be invariant of the some rigid space. Okay. Any questions so far?
What does it mean to say that it doesn't feel admissible?
This doesn't change up to weak equivalence.
Oh, okay.
Yeah. Any questions so far? Okay, so then I just give you some review on the rigid space. So, so just review. So for rigid space over K, so this is one of the several definitions, but this is the most classical one. So this is locally range the space like X, O, and equipped with some Grothendieck topology called admissible topology, which are locally the affinoid space. Affinoid space. So what are affinoid spaces? So it has appeared, like in maybe couple talk, maybe Kondo's talk. Well, anyway, so I give you. So fundamental things like a theta algebra. So Tn, so this is K of the T1 to the Tn. This is a formal power, this is a convergent power series. So this is multi-indices. So at nu, T nu. So this is the multi-indices, right? And this is in K, and nu is in a non-negative. And you ask this coefficient, so converge to 0 with respect to this and this norm. Okay? If this, like this goes infinity. So this is somehow like a power series, convergent power series on the unit ball. Okay, and affinoid is the so just quotient of these things as a ring, and any ideal is automatically closed. So you just somehow like this also like inherit this periodic topologies, and automatically A also like inherit the periodic topology. And you have like you can endow this any element of F as a so-called like supremum seminorm. So F, I mean usually like I omit A here, but this is now like this is a sup of the F. Okay, so I should end up what the space. So this is a ring. The space is the so this is a set of maximal ideals as a set. Okay, this is a maximal ideals in A. And it turns out that, like it's not completely obvious, but it turns out the residual field is all finite over the space field. Okay? So this means if you take any this point, cross point, okay? I mean maximally there on okay, and you look at this like this residue of this function at this point. So this lies in finite extension of this base field. And for the finite extension, you have a unique extension of the variations because this is complete. Okay? And that's like a unique extension of the norm. So you can somehow like evaluate this measure this guy element with this extension, unique extension. Okay? Does it make sense? So that's to give you some, actually you have to also show this is bounded and this is theorem, but that's a fact. And also I need a concept of the subring. So this is a model if it's open and bounded with respect to this seminorm. And this implies A0 is the periodically complete. Okay, so any questions so far? Please not hesitate to ask any elementary questions. Or advanced question, whatever.
Can you repeat the definition of a locally affinoid space?
Pardon?
Where in all of those symbols is the definition of a locally affinoid space?
No. Locally, this rigid space I somehow like obtained by gluing this space. Okay. Yeah.
So what's an affinoid space?
Affinoid space is the this guy as a set. Like this just maximally ideal in the affinoid algebra. Does it make sense? No, Chuck, I mean, locally means, okay, so maybe I was a little bit sloppy here. I mean, I welcome this kind of questions. Okay. So locally, with respect to this Grothendieck topology, are affinoid space. Okay. Sorry. I mean, I'm just... Any other question? It's okay? This is just basic notions in this rigid geometries, but if you fail to understand this now, like I don't think you understand anything in the rest. So I think I encourage you to maybe, I don't know. That's maybe too much to say. Yeah. Encourage you to make any sort of questions on this. No more question. It's okay. Okay. And so now, like I have to explain this topologies. So this is okay. So okay, let's say for if you have so this is the category of the affinoid algebra or affinoid space. Like I just identified. And also I didn't tell you what the topology is, but I don't tell you. I just tell you the Grothendieck topology. Okay. And so this affinoid algebra, and you take like a X, spec A. So this is just like a scheme theoretic spec A, and you take admissive blowout, any admissive blowout, which means like a blowout center, as I said, center is contained some power of pi. Okay? And you take some Zariski open covering of this. Okay, so this is Zariski open cover. Okay? And then then you take periodic completion. Okay? So this completion process makes really different this rigid geometry from object geometries. And so this, and you take tensor, maybe you just invert pi, that's enough. So that's AI. So this turns out, again, affinoid. And these administrative topologies are generated by the covering like this. This X. That's administrative covering. Okay? So, I mean, you have to notice that like this, I mean, this is not even finite type over A, okay? It's, even though it's flat, okay? So, I mean, it's really somehow like, this rigid geometries is really of different nature from the geometries. And so that's the definition. And the structure sheaf of the A on these things is just given like this. So that's a recipe for the structure sheaf. Okay. Any questions so far? But anyway, so this allows you to just somehow localize your object in a completely different way from the object setting, and that may allow us to more flexibility to approach any kind of problems. Okay. And definitions, but now in the setting we also important guiding principle is the descent. So this is a kind of administrative descent. Yes? A is affinoid. Yeah, this is the category of affinoid. Yeah. Descent. So this is so let's say E. So this is now pressure. Yes? So yes. Sorry. Yeah. Sorry. I mean, sorry. Sorry. You're right. So you take a model. Yeah. Sorry. Yes. You're right. And then you take admissible one. Yeah. Okay. So there are choices. Lots of choices. You also chose the models. I'm sorry. Thank you very much. Yeah. So let's see. Assume you are given some functor on a phase shift or functor in a value in spectra or any let's say D. This is maybe complete infinity categories. Okay, and so this satisfies descent. Satisfies admissible descent if for in these situations this natural map of this EA going to this homotopy limit of this E of UP. So this is the check nav. So you for this covering you get as usual you get the check nav, but so this is weak equivalence. That's the descent. And of course, I have to note like a UI. So this is open set, like a spec. Yeah, spec. SPAI. So this opens rigid open subset, and the intersection is just given by AI tensor AJ, but you have to complete it by periodic topologies. Yes. Yes. If for any A, for any U, yeah. And well, this is sort of maybe the fact or maybe theorem, but this is sort of very somehow follows from general nonsense. Okay, so this functor satisfies descent on affinoid on D. And is just equivalent, or the functor satisfies descent on the rigid space. I mean, this is not our theorem. This is just follow from the very general framework. Yeah.
What does U subscript
P, this is check knob, check knob. Like, this is the simplicial things. Yeah.
How did you need to be simplicial?
Just you have covering, in any Grothendieck site, okay? Then you can form some, for P simplicity, this just take a UI1, UI2, UIP or something, right? Yeah. But a product in a rigid space is just more complicated. You have to take completions. Any questions so far? It's okay. Okay, so that means if once you get some any invariant satisfying descent, it's automatically extend to the whole rigid space. So essential problem is to construct invariant on the affinoid space, satisfying descent. Okay. One, of course, also you can also by using this general some theories, you can somehow force your any theory on the any preceives on the affinoid to satisfy descent. This is sort of a simplification process, which exists in a general framework. But we don't take this path, okay? Because it's really involved the homotopy limit, and as Joseph explained, the homotopy limit is really difficult to compute. We really like to have some really computable invariant, okay? Maybe this. Do I really need it? My voice is, I think, loud enough.
No, it's not a microphone.
I see. Mm-hmm. Okay. So, so we just adapt different guiding principles. Okay. Maybe I just put this like this. Okay. So that's the homotopy. Usually object case theory, one guiding principle is the homotopy invariance. But in rigid context, that's not the right concept. I just introduced this pro-homotopy invariance. So, what's the pro-homotopy invariance? Pro-homotopy invariance. So, I think in the topologies, you have, Ki of topological case theory for the topological space satisfy this invariance with respect to the interval, right? But now, what's kind of a rigid? Some kind of a rigid analytic interval in a setting. And of course, you can think of, let's say, B1. So this is a suit of KT. So this is a unit disk. Okay? But there's examples. So this is due to Gerritsen. So that's, you take A to be a K, XY, and X square minus Y cube minus pi. And so this integral is also, you have integral model, like a KO, and same things. And integral model, even this integral model is regular. But the problem is a reduction. Mod pi is singular. And he showed this peak. This is just usual peak, okay? Peak of A going to the peak of a T is not surjective. This is not surjective. So, even this regular things, or even this model is regular, doesn't satisfy this B1 invariance, maybe the B1 invariance is not the right principle to follow. So what we adopt is that we replace, this is the fundamental idea, replace this AT, AT is just, this is the A cross B1, which is the, this is AN, TN, and AN, so this is AN is in A, this goes to 0. Something like this, okay? So replace this guy by flow system. So rho is real numbers greater than 1 and AT rho. Okay, so AT rho is now like you take this rho to the n here. So this is a replacement of the A cross this disk with radius rho. So you take bigger radius, and that's formed this like a flow system like this, and this is sort of a affinoid approximation. This rigid analytic fashion of A, whatever it is. You have a notion of the affine, rigid analytic fashion of affine line over A. But this is not quasi-compact anymore. And it's difficult to handle this kind of things. And instead of using this, we use this plot system. So this is the plot system. And our theorem is the following. Actually, in this case, for any regular affinoid, so this is a regular affinoid, this peak of A, and this is rim over rho, or the peak of AT rho. So this is the proiso. That's the theorem. So this, yes?
Your limit is over positive integers?
No, this is a real number, but like this, this which lies in the value of this norm of K. Value norm of K is a discrete. So, you cannot take all these real numbers, but just, can I write this? Okay.
Just as long as I understand what
Yeah. Okay.
No, I don't. I thought rho was tending to 1.
Yes, if rho prime is rho, then rho prime is AT rho. Because, you see, this is a convergent power series on the disk over A with radius rho prime. And this is same for this rho. So this convergence property is stronger here. So that's why this you have less convergent power series for this bigger radius. Does it make sense? Yes. 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 No. Intersection. Yes, union. In other space, union. So that's why this. Okay. Yeah. Okay. Any other question? Okay. And actually, we also expect some kind of, even this expect, we can replace peak by this isomorphic class of the vector bundles. That's sort of a rigid analog of the Bass-Killing conjecture, and which we couldn't prove so far, but we really expect this. But in the end of the talk, I just give you this evidence for this. We just showed it's kind of a stable version of this conjecture. Any other question? Okay, now we got this guiding principles. So let's follow these principles to define our gadget. So somehow we upgrade this in a flow homotopy invariance, the level of the spectra. but it's not quite possible to work in the frame of spectra. You have to work in the prospectra. And so for this, so this is the category of prospectra. And if you have map in this, so this is the weak equivalence. This is the weak equivalence if for any integers, this truncation, this is a level-wise truncation, okay, is essentially level-wise equivalence, which means like, I mean, up to, replacing isom in these categories. So this becomes level-wise equivalence. And this is equivalent, exists some n, such that this tau n is essentially level-wise equivalence plus pi star equivalence. Which means like, you can take a pro-homotopy group of this guy. So the now homotopy groups are pro-abelian group. And pro-homotopy group is isom as a pro-abelian group. That's what this means. Okay? Okay, that's about weak equivalence on this prospectra. Is okay? Essentially, this one is essentially level-wise equivalence.
What is it, tau less than or equal to n?
This is a truncation at level n. Of this map, okay, F. Yeah.
So there's two conditions. The first one is that
This is a strong conditions, like, up to isomorphism.
the first condition is that there exists an n such that the rest of the
No, this is for any n. So this truncation is essential.
You have pi star equivalence there. Is that part of the existing? Is that part of the whole thing, or is it?
Yeah, no. I mean, this is one part. This is the second part. Yeah, two parts. Yeah. I can give you some more kind of a conceptual, interpretation in terms of infinite categories, but I won't do this. And okay, so then we can talk about the pro-homotopization. So you look at this still in a pressure for the spectra on the aphenoid. So here you just consider full category, which satisfy the following conditions. So this is some factors such that this f of a for any a aphenoid, then going to this prospector, and this is f of a at rho. So this is weak equivalence. You can consider this subcategories, full subcategories. And proposition is this embedding has pro-left adjoint. Given by following way. I mean, maybe the experts know how to do it. But anyway, so this is like a F, PHI is just prospectra of a row of the H row of F, where H row of F of A is the, okay, you have certain simplicial aphenoid. And I will explain you in a minute. This is simplicial aphenoid of this radius row, and you take realization. So let me write this guy, f of a, just like this simply in the in what follows. And where this simplicial aphenoid is the following. So this is now row. So this is a. So this is this is x0, xn with rho, this, like this multivariable, this convergent power series with radius rho, and divided by this usual things. And the pro-homotopy, pro-left adjoint means, so this means this natural map from colim of rho, and this mapping space in this, in the functor categories, from this H rho of F to G. So this is for any F in C, any G in PHI. Let's say, so G. So this map to the, this F to the G. So this is the weak equivalence. Okay, does it make sense? Any questions? That's what the pro-left left adjoint means.
So that's a solution, F and O, you're applying F to it and then taking the realization?
Yes. 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 Okay. It's okay? Yes. Makes sense in infinite categories. Yeah. But, I mean, I don't know if this is really necessary or not. I mean, in the latest, like I have to take the colimit for the bus relooping, analytic bus relooping. There, I think we need the infinite categories because, like a colimit for the prospector is it's really awful. Yeah. May I proceed, or you like to ask a question? Yeah. Okay. Mm-hmm. Okay. I mean, so far, I don't think we need really, you use this essentially infinite categories. Okay. So that's, we have now really some kind of a very abstract nonsense to get this homotopy invariant, pro-homotopy invariant gadget. And so like, okay, so now I have this new first step is the, okay, so this is sort of the rigid analytic Calvi-Villamayer theory. So that's the KB. So this is KB-R. So this is, you just take a BGL, and you take a pro-homotopization. That's our first step. And the point is that this is really computable in a way, because, okay, so this is lim of the H rho of BGL. So what's this H rho of BGLA for the aphenoid? So this is, just BGL of the, this simplicial aphenoid, and take a limit of generalization. But now homotopy group of this is just homotopy group pi I-1 of the GL of this simplicial group. And so, for example, this implies KV1 of A is this is K1, usual algebra K1 of A divided out by following this subgroup. So this is 1 plus M. So this is the matrices in A such that M over pi rho is topologically nilpotent. Where, pi rho is any element whose norm is the rho inverse. And this just, KV and rho. Maybe, so this just denoted by this guy is KV and a rho. So this rho. And so the KV1, analytic KV1 is just pro system of this kind of things. In a way, it's very explicit. And the important information that I will use for the comparison of our analytic K0, analytic K0 we haven't got. We have to somehow deloop it, okay? But, after delooping, we get this analytic K0. And we're going to show this, actually, this analytic K0 is equal to the object K0. It's some kind of observation for the aphenoid. And for this, we really need this information. Okay, any questions so far? And the theorem, first theorem is the following. We already get this some nice comparison with the continuous case study at this level. Okay, so if assume A is regular, and I also fixed some integral model, and I assume some resolution singularities. Okay, so that's the exists some x proper and iso over spec A. Actually, A is the A0 of pi embodied. And X regular. Then, this our KV of A is weakly equivalent to the homotopic fiber, but you have to truncate of this K of A0 on pi going with this K continuous of A0. Sorry, this is A0. Does it make sense? I mean, truncation is always level-wise. Level-wise. Does it make sense? So we already get some, comparison of this analytic case theory with continuous case theory for aphenoid. Okay, scheduled proof. Maybe I. Okay, so we just fix J, and rho is now like a pi of the minus J. And we just take, we have this simplicial aphenoid ring, like these things. Okay, so we take the integral model of this. So AJ. So AJ is, this is AJ, is just a subring generated by power series A nu to the X nu, such that, A nu lies in like a pi to the nu J A0. So this gives the integral model of this guy. And, and that's okay, J dot. So J and rho is somehow like comparable. Yeah? Okay. And we get another simplicial ring like this. But, I didn't say that okay. Okay, okay. Maybe, how does it work? Any question? It's okay? Only 10 minutes left. Okay, so then, this is key lemma. So then we can show this as a pro spectra. I mean, I didn't say that, this guy is a connected simplicial ring. So even though I just took this BGL of these things, in the geometric realization, this is already infinite loop space. So you can upgrade it to the spectra, okay? Pro spectra. And but this time, this guy is not anymore connected at a simplicial ring. So you have to take a plus construction. So these things, okay. M, so this is BGL. And actually, this, you can show this, weak equivalence. Okay, and also you take this one and no, you don't. No, you don't need it. This is not the simplicial anymore. So this is just plus construction here. And this gives you okay already. So this is now just K, like a truncated continuous of the A0. So this gives us map from K truncated continuous A0 going to this our KV of A. Because apparently this goes to the limb of law of the BGL or AT law. No, these things. Because because as I said, this is already infinite loop phase. Doesn't change even if you take the plus construction here. Okay, so I only have 10 minutes left. I just wonder if I should give a proof of this lemma. Maybe I shouldn't. Actually, this is okay. So this okay. So I just say. If you ask me, I can explain you later. But this use first. Somehow this is reduced. Maybe I just give you some few words. So this is reduced pro iso of the BGL of the AJ plus constructions and the limb of the M. So you somehow you have you just note, you must have noticed you have a different index for the flow system already. Okay, and here so this is a little bit simpler. So this is the AJ. So this is the for fixed J. Pi to the M. But for this, so I don't have to process them here like this. For fixed J, we already have these things, and then also you have to use this, what was it? Yes, this map, natural map from A to the pi M, going to the limb of the J of AJ. This is a for fixed M to the A0 of the pi to the M. AJ of the pi to the M. So this is the isom of the pro-simplicial ring. And the lemma follows these two statements. And for this, first of all, to show this, first of all, you just use some kind of Isaacson's pro version of the Whitehead theorem to remove this plus construction. Okay, and you need some input from this some general machinery from in a pro-simplicial set, and that's due to Isaacson. And you can somehow remove this plus construction here. Then it's rather easy because now the homotopy group is just computed by the homotopy group of the simplicial group. And then this map from GL AJ dot going to GL AJ dot over pi M. So this is a configuration of the simplicial group. So the fiber is just computed the pi to the M, and the matrices of the AJ. That's a fiber. So what you should do is somehow this show this is kind of a how to say, equivalent to the zero process. What I mean is maybe I just say this. If you take a substance, actually M plus J is fine. So this inclusion, so this is null homotopic. That's the proof. And you can just construct this crystal homotopy for this. Okay, only 5 minutes left. Okay, so maybe, I don't know, I mean, what can do? So this is only, you know, connected part. You know, you have to deloop it. And the delooping is given by, usually in Azure setting, using, you know, like a bus construction was the, something like, yeah, 5 minutes. What can I tell you? Okay. Okay, so maybe I just skip this in like a maybe general nonsense, and I just give you some explicit bus delooping. Okay, so now like a KV arm is now like a passive on Aphenoid in the value in the plot spectra, and somehow this is, but now like this is connected, and we like to deloop it. And okay, recall what bus did, but like this time we use, let's say, so now this is now like a gamma, so for any some in like a perceived like this, gamma E of A is just usual. Maybe this is push out. Maybe this, I don't know if I have time for this. Okay, so we can deloop it. I mean, so that. Okay. So there is some general construction to the somehow like you know like a busification. So that like so this guy satisfied you know like a usual bus properties like A, T, exact sequence. Maybe I have to say in the spectral level this is A, and so EB. So this EB satisfy like this, and okay, plus sigma of EB A is equivalent to the E of A T inverse. And by you know like from this factor restriction. So first factor is restriction. The second factor is cut with T. So for this, we have to formulate some kind of this K-module structure. You know, like this subcategory of which is K-module. K is just usual killing K, you know, connective K series. And you have to define some LK, killing K, I mean K-module over killing K series of this. And for this, you have somehow like you know, like you formulate this as a bus fundamental theorems, properties. And you just construct, you know, like a left adjoint for this inclusion. That's a kind of same procedures as in the classical case. But you have to, this time you have to use this analytic, board, analytic disk, instead of the polynomial. Okay? And you can do this. And then our case series is this busification of this. Okay. So now main theorem is the following. But I have to warn you that for this busification, somehow you have to, I mean, you have to take a colimit. And as I said, the colimit in the prospectra is really awful. And they are, I mean, maybe I just tell you how awful it is in a minute. So now here's the main theorem, which I should say improve in 3 minutes. This is our KH, and satisfy this hand. So, I mean, it's automatically extend the whole rigid space. And how do I prove this? Okay, I mean, proof. in the previous theorem, I mean, in the previous theorem, I constructed this what was it? It was like a tau truncated in a degree, I mean, disconnected things, continuous from A0 going to the KV of A. That's what I constructed by this, this lemma using this pro version of the Whitehead theorem and so on. Okay, now you can take this de-looping stuff. I didn't say that. I mean, this is somehow like a case stage of the de-looping. Okay? So this you can compute. Even though this is sort of a case, this is the case stage of the de-looping, but it's analytic de-looping. But you can using excision. I mean, this is notation from the Chuck's books. And so this now you can replace usual algebraic bus de-looping, using polynomial. This is by excision. Okay, so K minus this one. And by bus fundamental theorem, this is the bus. So this is K, maybe minus K truncated of A continuous. This is all continuous. Okay? That's not so difficult. But here comes some difficulty in the prospector. Because now you can take colimit over K of these things. And okay, so you get these things to by just taking this lambda K of both sides. Okay? You get this lambda K of the KV of A. Okay, that's fine. And our KH is the colimit of these things over K. And you like to get this in a map from, so this right-hand side is just by definition KH of A. Okay? But now, you think, of course, I mean, if you take a colimit of this truncation, you should get this thing, right? But this is true, but not trivial. Because the colimit in the prospectora is not level-wise, doesn't commute to even the sequential commute doesn't commute with homotopy groups. And so this is not true in general. For general, this prospectora, this is not true anymore. And to verify this, need this Weibel's k-dimensional conjecture. Yeah, but that's not so, this is maybe using this. This is maybe not so difficult, but difficult part comes even after this. You have to compute this 5 of this. And I give you the computations. This will really hard work to compute this fibers, but actually you can compute, which looks like this, okay? I give you definition this. This is sort of the algebraic pro-homotopization of the homotopy case theory. Okay, so what this is? So this is the computation of the fiber. After many computation, you get this things as a fiber. So what is this is the algebraic things. Okay, this is the very algebraic, don't analytic things. So this A0 on pi is just fiber of the KH of pi infinity of A0 going into this usual KH of A. Okay, and what this guy? So this is prospectora given like this. So this is now realization of the K of the A0 of this polynomial, usual polynomial simplicity ring, but you just take, make some little twist here by pi j. So what this thing? So this is just A0, maybe just A0 of delta n of pi j is just A0 of x0 going to xn, but you just twist this equation by pi j. And that's form some kind of pro-simplicial ring. And that's what this is. And that's a computation of the fiber. Okay? And then using proceedage descent, using proceedage, proved by Morrow and Kurtz, Strunk, and Tame, this is upgraded for this atomistic blow-up to the kh pi infinities of x on pi and k continuous of x going to the kh of a. You can upgrade it to this model, this fiber sequence to this model. Okay, then, because administrative covering is just coming as obtained as a completion of the Zariski covering of this guy. And using excisions, these guys satisfy the sum for this covering by Thomas and Travaux. And that's how you show the descent for this guy. Sorry, I extended 5 minutes. Yes?
So your notion of homotopy invariance involves the analytification of A1.
Yes?
Rather than analytification of A1 as a pro system.
Yes?
But then when you pass the loop,
Yes?
you didn't use the same version of the line.
No, so, okay, that's a good question. Yeah, I mean, so that's where this averagization problems comes in. You see? I mean, this somehow like in order to, approach these averagization problems, somehow like, your things is just, like a bus looping of the pro-homotization, right? And I can show this satisfied pro-homotization invariance still using this fiber sequence. Okay? But now, in order to this, do anything about this averagization problem, you have to also study this defect of the pro-homotopy invariance, defect of the pro-homotopy invariance for the usual object case theory. And we have some plan, but this is now a very concrete problem.
So even if I have a regular model A0,
Yeah.
I might still have negative analytic KH.
Yes. Yes. Even this regular model, you may have some negative KH, analytic. Yeah. I didn't say you. I mean, this also another main theorem is a comparison of the KH0 and KH K0. So another theorem was the. So this is maybe first step to the observations. So K0 for a regular. For K0 of A is isos for the KH0. So for this, I mean, at least for regular Floyd, at least for KH0, you can somehow like a visualization. Somehow like, this element is represented by some honest projected module over here. I mean, it's somehow remarkable because this definition was really analytic and doesn't see any, chance to, to represent this element as some algebraic object. But still you can do this using this bus looping. And also, as I said, this, this explicit presentation of the KV1. Yeah. Thank you.